In this video, we're going to configure MPLS Layer 3 VPNs on the two PE routers, PE-R2 and PE-R7, and we're serving this customer called Acme Incorporated. They've got two sites, one on the left over here and one on the far right. First of all, we're going to jump into configuration mode and give this router, which is R2, a beautiful name. So once it has a beautiful name, we next need to create a VRF. Now, if you're going to create a VRF just for IPv4, you could use the IP VRF commands. But if you want to use version 6 and version 4 of IP, you need to use the VRF definition command. So that's what we'll do for the flexibility. Then after we create this VRF definition called Acme, we'll specify the route distinguisher that keeps that route and routes from this VRF separate in multi-protocol BGP from the other routes. And once we've specified a route distinguisher, we'll then go ahead and move into the address family configuration mode of this VRF for IP version 4. So basically, when BGP takes routes out of the VRF and puts them into multi-protocol BGP, it's going to attach whatever route targets are associated with this VRF on this router. So we're going to specify route target export values of 2020 on R2. So that when R7 imports those, he'll be importing 2020. So over here, we're going to do route target export of 2020. And then as far as when R2 takes routes from multi-protocol BGP and puts them into an import into the VRF, we're only going to import routes that have the route target that we specify right here as part of our VRF definition on R2. So we'll specify route target import of 3030 here. So we'll have to remember that. So when we go to R7, we'll have to do exports of 3030 because we're importing 3030 here. Now you can use the same number everywhere, but I wanted you to be able to see how they interrelate. All right, next we're going to go and globally enable MPLS so that if we want to enable interfaces for MPLS, it'll work. So that command's real simple, MPLS IP. Now the next thing we're going to do is set up a loopback interface that we can use for peering. So here on R2, we're going to create a loopback 0, specify a really easy to remember IP address. We'll add it to an IGP, OSPF to make it reachable, and we're going to use the IP address of 2.2.2.2 because it's R2, really simple. Next, we'll enable these interfaces. We'll go to interface gig 1/0 and give it a cool little description and an IP address appropriate for that subnet between R2 and R3. We're also going to enable MPLS on this ISP facing interface right here because we want LSPs, label switch paths, to be formed inside of the service provider network. So MPLS IP is all we need to do there. Going down to gig 2/0, we're going to go ahead and enable that with an IP address and MPLS IP. And beforehand, I took all these interfaces and I brought them up. So I didn't have to do a no shutdown. On a new router or an interface that hadn't been used, you'd also want to do a no shut as well. Now, last but not least, we're going to go to this interface, gig 3/0, and we're going to allocate this interface to the VRF. So in interface configuration mode, we're going to say VRF forwarding for the VRF called Acme. And then we're going to give it an IP address. Now, we're not done yet. There's a couple other pieces we need to put in place. We need to put in routing for the service provider. So the service provider, their IGP is going to be OSPF. We're normally going to see OSPF or ISIS. And so we'll use OSPF in this example, and I want to include the loopback interface of R2. So I'll do the network of 2222 to bring that into OSPF. And I'm also going to include both of these interfaces here, 10 and 20. They both begin with 10. So I can just do a 10 with a wildcard mask saying anything that starts with 10 is inside of OSPF. Next, we'll configure this blue line, which is the iBGP neighborship between R2 and R7. So we're going to use BGP 27 as our autonomous system number. I'll specify R7's loopback as my peer's address. And I'm also going to say I want to source these BGP sessions from my loopback 0. And that way we can have full reachability. And check this out, if we lose a physical interface, we still have some fault tolerance because we have multiple connections inside of the service provider network. Next, we need to tell this router R2 that we want to support VPN v4 capability. That is, taking the routes, putting them inside of VPN v4 routes inside of multi-protocol BGP, and supporting not just IP between R2 and R7, but also VPN version 4. That's a fancy way of saying VPN routes for version 4 as opposed to VPN routes for version 6. So we're going to activate our neighbor for VPN v4 capability, and we're also going to make sure we're sending the community. So once we've done that, we're still in BGP. We also need to make sure we're going to correctly export routes from RIP, which we're going to use with the customer, into BGP. So what we're going to do is we're going to say address family IPv4 for VRF ACME, redistribute RIP, and that's an export, my friends, pulling routes out of the ACME VRF and into BGP, specifically RIP routes out of the VRF. So last piece, we need to go ahead and configure RIP to operate between R2 and the VRF and the customer. So we go into RIP configuration mode, go further into address family for the VRF called ACME, and we simply specify the details that we want to do. In this case, we're going to redistribute BGP. That's pulling routes from BGP into RIP, and we're also going to include all the networks that we have at 172.16. Now, in reality, R2 only has one interface that belongs to the 172.16 network, and that's this guy right here. So we could have said network 0000, and that would include all interfaces that are assigned to the ACME VRF. So we're including that route, and now we're sharing routes back and forth with R1. So that's it. Piece of cake, right? Let's take a look at how we would verify some of the pieces so far before we jump over to R7. In fact, let's go to R1 and take a look. So on R1, what should we expect to see? This is the customer site. If we do a show IP route, we shouldn't be too disappointed yet because we haven't really shared anything yet. R7's not configured yet. So even if R8 was advertising routes over to R7, because R7 hasn't been configured with BGP and everything else, R2 has basically nothing to share. But what we could do is back on R2, we could say, let's do a show IP route for any routes in the VRF called ACME. And I need to spell ACME right. ACME, not acne. All right, and we do have a directly connected route. That's this interface 3/0, and we also have a RIP learned route. That's a loopback interface on R1, the 172.16 1.1. And we could probably ping that. If we do a ping VRF ACME and ping 172.16. What is the IP address? Let's go check the IP address real quick. Show IP interface brief. It's this guy right here, 172.16 1.1. So if we ping that from the correct VRF, and that's a really good indicator that our VRF component is working. We could also take a look at multi-protocol BGP. We show BGP, VPN, v4, unicast, all, and that'll show us all the routes, all the multi-protocol VPN, v4 routes that we have. And we have this network right here, and the 12 network. So the 12 network is between R2 and R1, and this network is the loopback. Now, routing commands, things are changing. So we could use this command here, but we could also use an older command that does the same thing, show IP, BGP, VPN, v4, all, and that would give us the same result. So this command and the command with the word IP in it, because I still have IP enabled for version 4 for BGP, it both show us that same information. So that's a lot of fun. What have we accomplished? Really, nothing yet, because we have to configure R7 to do the same game. So let's make a road trip over to R7 and configure him with OSPF, with BGP. We'll enable MPLS. On this side, we're also going to use EIGRP to interact and share routes with the customer as well. All right, so here we go on R7. These interfaces have been brought up, so they're not in a shutdown state, but everything else needs to be configured. So let's begin. On R7, we'll jump into router configuration mode, or configuration mode, give it a host name, and enable MPLS IP, and create the definition for ACME. Just like we did before, a little bit faster this time because it's the second time around. Now here, we're going to set the route target export of 3030. That's because R2 is importing 3030. So whatever we export, the other side needs to import, and vice versa as well. We're going to set our route target for imports of 2020. Why? Because R2 is exporting with the tags or the extended communities of 2020. So you could use the same number on both sides, but I wanted to mix it up a little bit so you could see the correlation. What one side exports, the other side needs to import. Then we'll specify our loopback interface for reachability. We'll make sure we put that in a routing protocol as well. And we can then enable our interfaces. So we'll go to gig 1/0, which goes to R5 right here. Give it an IP address, enable MPLS on it. We'll go to this interface, gig 2/0, give it an IP address, enable MPLS on it as well. And then we'll go to interface gig 3/0, allocate it to the VRF that we created, give it an IP address, and again, it's not shut down, so it doesn't need to be brought up. So that part's all good. Now, what about the routing for our ISP? We need to enable OSPF. So we'll set up OSPF and add the loopback interface and these two 10 networks. That's all good to go. And then we also need to set up the routing between R7 and R8. So we're going to go into router EIGRP1, and then we're going to go into the VRF related configuration. This is a little bit tricky for some people because they haven't seen it before, but inside of the address family for IPv4 for that VRF, that's where we set up the network statements. That's where we set the redistribute command to pull the routes from BGP. And also this next line right here, this is so critical. This number right here has to match the actual AS number that the customer is using. So even though I started off with EIGRP1, we need to specify the autonomous system inside of that address family for that VRF that the customer is using. Then the rest is similar to what we did on R2. We're going to specify our BGP. We're peering between R7 and R2. We're activating the neighbor for VPN v4 capabilities. That's not news. And then we're also going to make sure we export the routes from EIGRP. So we're going to specify an address family for IPv4 for the VRF called Acme that we want to pull any of the routes that are associated with EIGRP8 and pull them into BGP. So that's an export from the VRF into multi-protocol BGP. Now we should, in a few moments, have some activity here. R7, we should be having a BGP neighborship with R2 if the routing is all correct inside the core of the network. So let's just do a quick couple of verifications. Let's do a show IP BGP summary. Oh, that's good. I didn't notice that message popped up. So we've got our BGP neighborship. Now, this is actually showing us the IPv4 unicast neighborship information, which we're not too concerned with. But let's do a show IP BGP VPN v4 BGP V. Oh, I see. It could be VPN v6 or 4. I didn't put all the information in. And we'll say all. Now, what this command is doing, and I could have typed in show BGP VPN v4 unicast all. That also would have worked. That's showing us all of the VPN v4 routes that R7 currently knows about. And it knows about this guy. It's directly connected to it. Not a problem. And it knows about this one. And that is the 192.168.8 network, which is a loopback. The next hop is R8's address. And then we have two remote BGP VPN v4 routes that we've learned from our good buddy R2 over here. So if everything's working correctly, let me just verify the IP address over here on R8. Let's do a show IP interface brief. And he's got, yep, there's his loopback right there. Let's go ahead and do a trace all the way from R1 through the MPLS network all the way to R8 and see if that works for us. I hope it does. That'd be awesome. So let's do a trace to 192.168.8.8. Oh, I love it when a plan comes together. So let's just trace this and identify what happened. The first hop was from R1 to R2. The last octet, by the way, matches the router number on every single device. So the next hop after that was R3. So based on the IGP and the way MPLS decided to build the label switching path, R2 is forwarding to R3. And if we look at the next hop, it's going to R6. That's interesting. So it's going from R1 to R2 to R3 down this link to R6, and then it's going to R7 and then out to the final customer at R8. And there's the labels that are being imposed, pushed, and popped along the way. Wow, That's pretty cool. So let's see about fault tolerance. If we are using this path that includes R6, let's go ahead and shut this interface here on R6 down. Now that interface is gigabit interface 3/0. And we could verify that as well. Well, here, based on this IP address, the 36 subnet is between R3 and R6. So I know it's this interface right here. We could verify that by going to R6 and doing a show IP interface brief. And sure enough, there it is, gig 3/0. So we could actually shut this down with a quick shutdown command. So now this interface is shut down. If we go back to the customer and we try that same trace again, my hands will never leave my arms. Check this out. Now it went from, started at R1, went to R2, and then it went to R3, and then instead of going to R6, because that interface is down, it went to R5. So the convergence is very fast and fast. The limiting step, the biggest time taker in converging a fault-tolerant network like this one with multiple paths is your IGP itself. So let's go back to R6 and heal it. We'll do a no-shut on that interface. And it'll bring up the interface, and if there's switches involved, there might be some spanning tree issues of convergence and so forth. But after a few moments, we should have our full connectivity back here again. One of the other fun things we can do is we can actually change the labels that are being used. So if we want to see some very different labels on R5, for example, and R6, R3, we could actually take off MPLS, put it back on, and it would continue to increment the labels and make them higher and higher. So let me demonstrate that real quick as well, just for fun. This would not be a good idea in any production network, because if you remove the labels, you're going to lose your label switching path across the way. So on R4, well, actually, here's what we could do. Let's go to R3 and just do it across the board. We'll do a no MPLS IP, and it's not going to like that. MPLS IP, and we'll do it a couple times. So we'll say no, and then we'll say yes. I just want to show you how it can increase the number. So if you're building a lab or practicing, and let's do a trace again, and you can see the labels that were used previously inside of the service provider network. If we do another trace going through, we'll notice that the labels are significantly different. So here we impose a label of 41, and that's because R3 had increased his local label to 41 based on the changes that we injected. And then it looks like we are going from R3 to R5, and we didn't make any changes on R5. So his labels would be the same. So that's a good way you can verify it. So as a summary of how this operates, is the customer advertises their routes via any routing protocol you darn well please. It could be BGP, it could be ISIS, it could be OSPF, it could be RIP or EIGRP. They advertise their routes over to the provider edge. The provider edge receives those in an interface that was allocated to specifically a VRF for that customer. When those routes are taken and put into BGP along with the export route targets assigned by that router, they become VPN version 4 routes. If we were using version 6 of IP, they would be VPN v6 routes. It's very similar in that process as well. R2 is going to advertise these VPN v4 routes over to its good buddy R7 with its own next hop. R7 is going to take those routes from multi-protocol BGP and import them into the VRF on the local router. Once they're in the VRF, they're advertised via EIGRP over to router 8, who now knows about those remote networks. This same process, by the way, of the control plane happens in the other direction as well, with R8 advertising his routes, getting those put into multi-protocol BGP, advertised over to R2, and R2 advertising them through the VRF through the local routing protocol. So it's RIP over here, EIGRP over here, and then we have a label switch path where these routers all in the middle, R3, R4, R5, and R6, have no clue about these customer routes. All they know is how to reach the edges of the network, and they're doing label switching between them. So if we took a peek at, let's say, R5, and we did a show IP route, we'll show everything in the IP routing table. You'll notice there's no 172 networks at all. There's no 192, 168 networks. because primarily these guys are label switching between the IP address of 2222, which is R2's loopback, and 7777. So if we go back here, back to R1, and we type in telnet over to 192.168.8.8, which is the loopback interface over here of R8, the entire traffic is label switched across the service provider network. They have no clue, but we still have our full connectivity from site 1 over to site 2. So I've enjoyed walking you through the configuration of MPLS. For those of you who want more information on it, there was a presentation I gave at Cisco Live in 2011. Cisco, I believe, has that available online. So if you do a search, I think you can find that and get access to that as well. It's been great having you. Have a great rest of the day. I'll catch you in the next video.